Welcome back. So in this video, I wanted to do a nice analysis exercise. What I want to show is that the sequence x to the n is not uniformly Cauchy on the compact interval from 0 to 1. Okay, so for a reminder of what it means for a sequence of functions to be uniformly Cauchy, so have our sequence of functions, fn. We say this is uniformly Cauchy on, let's say, a. Generally, this would just be an interval if for all epsilon bigger than 0, there exists a natural number big N such that for all n and m greater than or equal to big N, and also for all x and a, we have that absolute value of fn of x minus fm of x is less than epsilon. Okay, so this is different from being Cauchy at a point. Being Cauchy at a point basically just means that you have pointwise convergence. This is for all x in a at the same time. So if you pick an epsilon, you can find a big N, and it doesn't matter which x you pick in a. This is always true when n and m are greater than or equal to big N. Okay, so our goal is going to be, suppose that such a big N exists. So suppose that there's a big N that satisfies this definition, and we basically want to find an x such that absolute value of x to the big N minus x to the m is greater than or equal to epsilon for some m greater than or equal to big N. Well, okay, I guess probably strictly greater than big N. So this will show that the uniformly Cauchy criterion basically breaks. We can always find an x that will make it not work. Okay, so how do we do this? So first, we're going to note that since x to the n is a continuous function, basically, draw a little picture here. What the x to the n's kind of look like is something like that, right, on 0 to 1. Okay. So we can find delta 1, let's say, such that if x is in the interval 1 minus delta 1, 1, then the following is true. Absolute value of 1 minus x to the big N is less than delta, okay, for any delta greater than 0. Okay, so just to explain a little bit what is going on here, I mean, I guess we could specifically say that this is true for x to the big N, right? So because x to the big N is continuous, if I pick a delta greater than 0, I can make x to the big N close to 1. This is just the definition of continuity. And where does this happen? It happens on this interval where x has to be quote-unquote close to 1, right? So it has to be bigger than 1 minus delta 1. So it's kind of in a little interval like this. Okay, I'm going to start a new page. Okay, so now we know that we can do this for x to the big N. So we know that we can make x to the big N close to 1, where close means less than delta. And this means that negative delta is less than this difference. That's less than positive delta. And in particular, this means that 1 minus delta is going to be less than x to the big N. So basically, what this shows is that if I want to make x to the big N close to 1, and specifically if I want to make it bigger than 1 minus delta, then I can do that. But reminder, right, our goal here is to get x to the big N minus x to the m to be greater than or equal to epsilon. And we want this to happen for some m that's greater than big N. Okay, so the idea is we should make the x to the m very small. Okay, so the next step, choose m greater than big N so that what happens? Well, so that x to the m is less than delta. And again, delta is just any positive number, but we'll choose a specific delta pretty soon. You know, we know that we can do this. Well, okay, so I guess something that I should have done first was why don't we fix x naught in this interval? Right? Because, so we're doing this at a specific point now, right? So we want to pick a specific x naught so that we're in this interval where x to the big N is bigger than 1 minus delta. Yeah, and then that allows us to find a little m so that this is true. And this is basically just because point-wise, you know, our sequence x to the n is going to 0. And I guess, actually, you know, I have to make multiple corrections here, but we're not gonna, this isn't gonna work if x naught is 1. So x naught has to be properly in this interval. Okay, but this gives us what we want, because then we have that x to the n minus x to the m, you know, again, x to the n we know was bigger than 1 minus delta. And then, sorry, this should be x naught. And our x naught to the m, we just figured out was less than delta by our choice of m. So that means that this difference is bigger than 1 minus delta, okay, which is 1 minus 2 delta. And I guess we should note that we can actually have absolute value bars here, and it won't actually change anything. And that's basically just because, again, this sequence is point-wise decreasing, right? So at any point, like, if I let my n get larger, then my x to the n sequence is going to do this, right? So this is what's happening to x to the n as n is going to infinity, right? It's kind of like getting compressed down. So that's why, like here, when I'm like x naught to the big N minus x naught to the m, this is a positive number. And so the absolute value bars don't really change anything. So, you know, the ultimate goal was to make this greater than or equal to epsilon. And so finally, we just choose a delta so that 1 minus 2 delta is greater than or equal to epsilon, right? And we can totally do that. I mean, explicitly what delta needs to be is, I guess we need 1 minus epsilon to be greater than or equal to 2 delta. So So delta needs to be less than 1 minus epsilon over 2. Yeah, so that's explicitly what the delta needs to be. But so the point of this is that we found an x naught, right? We found a point somewhere in the interval from 0 to 1 where this difference, x naught to the big N minus x naught to the m, is greater than or equal to epsilon, right? Because this is now greater than or equal to epsilon. And that means that this sequence isn't uniformly Cauchy, because we just showed that we can do this for any big N, right? The big N was arbitrary. So yeah, so that's basically the end of this proof. I guess as kind of a final comment, you can notice this implies the following. This implies that x to the n is not Cauchy with respect to the sup-norm. So, you know, if you don't know what that is, the sup-norm is basically just it's generally written like this. So you put in a function f, and the sup-norm of f on, in this case, the interval from 0 to 1, is the supremum of the absolute value of f of x, where x is in the interval from 0 to 1, right? So this is like potentially the maximum value, but at the very least the supremum that this absolute f of x achieves, right? And so we just showed that if I take the absolute difference of x to the n minus x to the m, I can always make this greater than or equal to epsilon. And so that actually implies that the sequence is also not Cauchy with respect to the sup-norm. So yeah, and that is basically the end of this exercise. So that's going to be it, and thank you very much for watching.